Thank you. Good afternoon to everybody. I'm glad you've come here to see my presentation, which will be about building a Kubernetes environment for multimedia streaming platform on AWS while keeping the latencies at minimum. First of all, let me introduce myself in a little bit more details. So, over the past 10 years, which I'm working in IT, my main focus was to build a platform for our customers to run their applications mainly in cloud. I have a passion in standardization and process automation, where my key ally is Terraform. And if I'm not spending my time with my family, then I'm probably playing football or doing some chores around the house. For the past couple of years, I'm working for an amazing company full of cloud and Kubernetes experts called Labyrinth Labs. In Labyrinth Labs, our main mission is to build a robust, scalable, and cloud-native platform. We call this platform Lara. And Lara is currently operating more than 100 Kubernetes clusters for more than 20 customers. And for the last year, we were also awarded as a consulting partner of the year for EMEA region, so for East and Middle. So that's about the formalities. Let's go to the main topic of this presentation, and that's building the high-performance multimedia streaming platform on EKS. To better describe the use case, I will give you some hints. What is it about? How the platform should look like? So basically, what we had before or in the beginning was that the application, the multimedia application, was designed in a microservice architecture. It should run on our Lara platform. So this means that the majority of workload should run in EKS. And also, this multimedia streaming application should also leverage some of the AWS managed services like RDS, Elasticache, or other. And of course, one of the key requirements for the application was to have it highly available. So it means that we have to actually use multiple availability zones, but for cloud native application, it's quite common these days to have it multi-AZ. Some key attributes for the multimedia streaming application. Sorry for that. Some key attributes were that the application was very latency sensitive, so that's why every millisecond counts. Also, the internal and external communication requires a lot of network throughput, and for the external communication, also there was a requirement that the platform itself should be able to handle a massive amount of active connections. Another attribute of the application is that the majority of data transferred between the microservices were in form of short-lived connections. Well, this is pretty important as we get to the problems that we have during the implementation. And everything that we implemented on our test environment looks promising until we started with some performance testing. On this diagram, you can see how the external communication is implemented. So I think that it's a standard way how to design an external communication to your backend pods. So in this case, you have an external load balancer in AWS, which is load balancing traffic to NGINX Ingress pods, and then NGINX is routing requests based on the path or on the host name to backend applications. So here you can see that the DNS resolution is mainly done by Cloudflare, because we are using for the multimedia streaming application, we are using Cloudflare. So that's where also DNS is being handled. we had to use multiple external load balancers, and that's because we wanted to handle hundreds of thousands active connections, and there is actually a not written limit for network load balancer that it can handle only a certain amount of active connections. And the encryption for the external communications should be end-to-end. For the internal communication, it's quite similar, except you are communicating within the VPC. So we are using Rules 53 as a DNS resolution or DNS resolver. The internal NLB is then load balancing internal traffic between NGINX ingresses, and also we had to deploy multiple ingresses in order to handle all the workload that is going through. So, as I mentioned, everything looked promising until we started with performance testing. So what was the problem? The problem was performance itself. But we can go through all the problems together because there are like multiple and in a different fronts. So what we have observed during the performance testing was that the communication, mainly internal, had a high latency. So it wasn't sufficient for us. Also, the network throughput wasn't sufficient as well. And we kind of observed that some part of traffic is being lost miraculously. So it was kind of a magic for us. And we also observed a high error rate for our applications. But it's quite understandable that we have a high error rate when you are missing traffic. And the overall platform performance was degraded. And while we were trying to debug the current state of the application or of the platform itself, we realized that the monitoring we had in place, which was basically standard monitoring based on Prometheus metrics which are available, and also on metrics provided by AWS, we realized that the monitoring is not sufficient, so we had to improve there as well. So, as I mentioned, those were the issues. So, what were the limitations that we actually found in our platform? First one is AWS instance and the selection secrets about it. So when we were actually debugging the platform, we realized that the workload is not improperly distributed. So, for example, we have all the microservices in one node pool. As guys before me described the Carpenter, we are using Carpenter as well. And we had only one node pool for all the workload, even though there were applications that required, or services that required CPU, some services required more memory, and some services were more network heavy, let's say. So we had to also do some deep analysis together with the customer to actually get a better distribution. So in the end, we divided it to more node pools, either based on some logical separation, so based on what the application is actually doing, or if the application needs more security measures or not. And we also divided it by resource requirements. So in this case, CPU or memory intensive or network intensive, because, for example, you don't want to have too many network intensive services together. But I will talk about it in a minute. When we were actually checking the network heavy instances or network heavy workload, we realized that there is a significant difference between AWS instances that have network throughput defined as up to a certain amount and instances with network throughput defined as the actual amount. So the word up to is actually, or means that's a burstable ceiling that the instance can burst during some time. And when you are bursting your instance, you are bursting also. You are taking also the burst credits. And once you are out of your burst credits, then you will drop to an instance baseline, which is actually a throughput that is not very well documented in most of the instance types. And when you are on the baseline, then the network throttling begins, and you are starting losing your packets. As I mentioned, AWS does not disclose the baseline limit for most of the instances for some reason. We don't know why. And the other observation that we found about these kind of instances is that not only size matters. So in this case, we had to also start using network optimized instances that are having AWS Nitro cards. Those are instances marked with N prefix. So for example, C7GN, so Graviton instances, but network optimized. And these kind of instances provide much higher network throughput than compared to standard instances. All right, so that was one of the limitations. Another one was Kubernetes itself. So in Kubernetes, as we had CPU or memory heavy instances, for CPU and memory heavy services, you can define some requirements for every pod. For example, you have a pod that is CPU intensive, so you can define resources for that pod, and based on that, a scheduler will actually schedule it to actually have that amount of CPU on a specific node. But for network throughput, you are not able to do so right now. So Kubernetes currently doesn't support to specify actually network throughput as resource reservation. So that was a pity. And that's why we had to do it in a different way, maybe a little bit dumb way, I would say, but we had to calculate how much traffic or throughput every pod requires, and based on that, we had to put only a certain amount of pods on a node, so the node won't be overwhelmed by the throughput required. But there's another limitation of Kubernetes, and that's there is no process or tool how to specify the certain amount of pod replicas on the same node. You can do only you can specify that by only requiring certain amount of CPU or memory and count it together, so it will just fit enough to a certain instance. In this case, you need to count with demonstrated overhead as well. All right, so another limitation that was a problem for us was kube-proxy. Kube-proxy is a network proxy for Kubernetes, and what it does, it basically maintains network rules on a cluster nodes. And kube-proxy you can deploy in multiple modes. The default mode is IP tables, but you can deploy it in NF tables mode or IPVs. Every mode has some different impact on latencies. So in the next slide, I will show you a quick chart about it. But those are the modes that you can use in kube-proxy. And if you don't want to use kube-proxy at all, you can use Cilium in the kube-proxy replacement mode, and Cilium in this case will use eBPF under the hood, which is actually the fastest way how to do the networking on a node. All right, so the following table shows the different modes of kube-proxy and also the Cilium as well, and you can see what are the overall latencies based on the mode and some details when it's the best to use the certain mode. So from the table here, we can see that the default IP tables mode for kube-proxy, which is the oldest one or the first one that they implemented, it has the highest latency from the old ones, and the lowest latency has the Cilium with eBPF. So if you want to have a fast packet processing, then you just go to Cilium and replace with proxy, kubeproxy. Okay, another problem, except the latency with IP tables mode, is that if you use IP tables mode, then and of course in our platform we used many short-lived connections, like hundreds of thousands, then you need to take into account the connection tracking limit. Connection tracking limit is a concept, or a networking concept, where a network device needs to track the information of IP traffic going through. And this kind of tracking is CPU intensive, and that's why there is a limit on connection tracking, because you have only a certain amount of CPU available for your instance or for your node. So once you hit the limit of connection tracking table, so the connection tracking table will be full, then the node itself is not able to handle new connections. So that's also a way how to drop your packets, or just to drop your workload data. And how to fix this? There are possible two ways. Either you can three ways. Sorry, you can either increase the limit. The limit itself is calculated like default number of entries times the number of vCPUs you have for your node. So either you will increase the default number for your vCPU, or you can just scale your instance to a bigger instance, and you will have just bigger connection tracking limit. Or you can get rid of connection tracking at all by removing kubeproxy and replacing it with Cilium. That's the way as well, and that's probably the fastest way. All right. When we were debugging the problems during the load testing, we also found out that the DNS setup that we had there had some limitations as well. And that was that we observed that DNS queries take too long, actually. So when we were debugging that, we realized that our DNS server placement wasn't correct, and also the DNS resolution within the container wasn't correct as well. So let's talk about it in a bit more details. So if you are using Kubernetes in AWS, so EKS in this case, by default you are probably deploying CoreDNS as kubedns inside your cluster. So every query that you are doing inside the cluster is going through the CoreDNS, which is usually deployed in a highly available setup, 3 replicas, for example. And this CoreDNS is then forwarding those requests to VPC DNS, which is actually DNS within the VPC you have. But this works for the most of the workload, so you don't have to take care of your latencies for your DNS queries. But if your workload is latency sensitive, that's also the case where you need to tackle that. So in this case, when you have only 3 CoreDNSs in your cluster, which might be on a different node or on different zone either, it's for your application, it means that it's just too far from the application. So in this case, what you can do is to deploy node local DNS. And node local DNS is essentially a CoreDNS deployed as daemon set in your cluster. So it means that it runs on every node, and actually it's the closest place where you can deploy your DNS, unless you want to deploy it as a sidecar or something like that. So we choose to deploy node local DNS on every node, and we also play around caching and TTLs on node local DNS and CoreDNS as well. So this way we were able to, by implementing caching, TTLs, and node local DNS, we were able to lower down the actual latency on DNS queries by, I don't know how many %, but quite a lot. So the final DNS path is now looking like this. So we have a node local DNS running as a daemon set on every node, and if there is no entry in the cache, then it will query the DNS or the host name from the CoreDNS, and if that doesn't have the information, then it will query the VPC DNS. All right. The second problem with DNS setup was DNS resolution inside the container. So for every Linux container, the DNS resolution is driven by ATC resolve conf. And if you are familiar with ATC resolve conf, there are like 3 properties by default. The first one is the name server you are having. If you are having deployed the node local DNS, then the node local DNS IP is a name server IP. Then you have your search domains, and you have the ndots property. So for the search domains, it's basically the list of domains every resolver needs to go through in order to resolve the actual host. And ndots means the number of dots in your host name in order to actually that the resolver needs to go through in order to do a final query, right? So to better describe it, I will show you this example. So my application is trying to query Aurora RDS endpoint. You can see there that there are like 4 dots in the host name. So if your ndots is set that with 5 dots, then you need to traverse all the search domains in your until you get the right result, right? So it means that if your ndots is set for 5 and you have less than 5 dots in your host name, then the result or the query process need to go through 5 queries, right? So it takes 5 times more time to resolve anything in order to get the actual IP where to route my traffic. So to fix this, we changed the ndots setting, and we changed it to 1. So every query will be queried directly, and therefore doesn't have to traverse all the search domains that were set in the resolve conf. And there is one problem with this setup. If you are using ndots1, then you are not able to resolve your local cluster endpoints. Like you can resolve a full cluster endpoint, for example, service endpoint, but you are not able to resolve only if your application or service is called myservice1. Then if you will do query myservice1, then this query won't be successful because it doesn't traverse all the search domains, right? So in this case, you will have to specify the full path for the service, like myservice1 namespace service cluster local. In this case, it will work. All right. So also, when we were debugging all the issues related to performance problems, we realized that the load balancing was one of the problems as well. So if you remember the architecture for the internal and external communication, there are some network load balancers in place, and behind those network load balancers there are NGINX ingresses, which are routing traffic to certain backend pods. And if your NGINX ingresses, or if NGINX ingress deployment is not evenly distributed across AZs, then there is a problem, because by default, network load balancer is always trying to proportionally load balance traffic across the assigned AZs. So if you have 3 zones, and for example, you have zone A with 2 pods, you have zone B with 4 pods, and zone C with 6 pods, and the load balancer is trying to load balance evenly across all the 3 zones, then you can see that the zone A with 2 pods is obviously overloaded. So you can see that those 2 pods are being under stress, and some latencies might be involved with that as well. How we resolved it? We resolved it in a way that we implemented a mechanism called topology spread constraints. So in topology spread constraints, we define that the deployment should be evenly distributed across some failure zone. So in this case, it was or failure domain, and in this case, it's an availability zone. Okay, so this is an example of topology spread constraint with 2 topology keys. First key is actually defining that if the scheduler is trying to place pod, it should place pod evenly across AZ, and it means that it shouldn't schedule more pods in the same AZ unless necessary. And the second topology key says that okay, I should schedule my pods across all the nodes, but if there isn't place in a new node, I can place it on the same node multiple pods or multiple replicas in this case. Okay, again, back to the limitations. As I mentioned in the beginning, we were using end-to-end encryption, so it means that we were doing termination on multiple infrastructure parts. So in this case, we needed to define the balance between security and low latency, because if you are doing end-to-end encryption, then you probably need to take into account that the encryption and decryption on every step of the infrastructure takes some time, and therefore the latencies will just grow up. So yeah, so that's why we did some basic benchmarking, and in this table you can see that if you are doing your TLS encryption from Cloudflare to NLB, so the TLS termination is done on on Cloudflare, then the application connection is taking from 49 to 63 milliseconds. If you are terminating your TLS on NLB, it's taking 5 milliseconds more. And even if you are terminating up to the NGINXs, then it's taking 7 milliseconds more. So here you can see that the TLS termination will also increase your latency for the communication. So that's why you need to choose between the balance of the security and also low latency. And yeah, and as I've mentioned previously, our monitoring was quite enough for the majority of the workload that we are serving for our customers. But in this case, we realized that it wasn't sufficient, because during the debugging process, we weren't able to find any issues. So we had to improve the monitoring first, and after that we were able to see where are the possible issues. So the best tool that we actually used for all the or majority of the networking issues that we had was to implement ATH tool collector for network performance metrics. It's a collector that is taking metrics directly from the node, and it's exposing metrics like bandwidth in allowance, bandwidth out allowance, contract allowance, and packets per second allowance. Those are all the metrics that might show you that there is something wrong with your instance. Either there is the instance is under heavy load, or the packets per second isn't sufficient, or you are hitting some connection tracking limit. On the following diagram, you can see the bandwidth in allowance exceeded. So it means that the instance was under heavy load, I mean network-wise, and we were hitting the burst limit for certain time. This kind of metric is not visible by default, so you just need to enable this ATH tool collector. And also here you can see that in certain times there was the instance itself was overwhelmed by the packets arrived on the interface. So you can see that there is an overload and some packets might be dropped. All right, so for the final solution, what were the key changes? So we first of all, we improved our workload, right sizing, and placement by dividing it to multiple node pools. We also, for every node pool, we did a proper instance selection. We also optimized the queue proxy by increasing the limit for connection tracking by per vCPU, but we are planning to implement Cilium in queue proxy replacement mode, which should even more help us with latencies. We did all the DNS optimizations that I mentioned during the presentation, and also we optimized the TLS setup, so we are not doing full end-to-end TLS encryption, but only from the client to NLB, for example. And also we drastically improved our monitoring, so we are able to see any issues in the future. So by these changes, we were able to hit the throughput for external and internal communication around 20 gigabits per second. Latencies went from, I think that from 500 milliseconds for internal communications to 250, and for external communication also we went from 100 to 254. So it was a drastic improvement for us. And currently we are able to handle like 20K requests per second for internal communication, and we have more than 500,000 external active external communications, so connections. So it's quite a lot if you are taking into account that you are going through NLBs. All right, that's about it. Any questions? I will have to. Yeah. All right. First question is: do you also use topology-aware routing with zone hints to further reduce the cross-AZ traffic? If not, this could further reduce the cost and improve performance. Actually, we are in a way of implementing it, and we were testing it quite a lot right now, and we realized that you can use topology-aware routing, but it's not very useful for a dynamic environment. So if you are scaling quite a lot up and down, then it's not very sufficient for that. So that's why we are currently looking into traffic distribution, which also uses topology-aware hints, but there is a different mechanism behind it, how to gather the backend pod. Have you tried DNS record terminated by dot? For example, Google.com, to prevent n-dot search on domains you knew won't change, won't need to be run through search domains? If yes, what were the drawbacks? I'm not sure about this one. I think that currently we are using N.1, so we are actually calling or querying it directly. But I'm not sure if I understand the question, to be honest.
I think I can explain. I didn't write it, but
Yeah.
the question is, if you are querying google.com dot, it will not run through the search domains.
Yes, but it's the same as if you set up the N.1. It's completely the same process. Yeah. Why is external communication latency higher than internal one? Internal one was 250 and external was 50, I guess. So it's the other way around.
Sorry, why was the internal latency higher than the external one? Because the network is usually that internal systems work faster than the communication outside of the network.
Yeah, that's basically the nature of the application, I guess.
Okay.
Okay, thank you.